This conference is about getting humans on Mars and let them thrive there. Our next speaker, however, is thinking far more in the long run, searching for a way to go beyond by knowing the universe better, much better. With Avi Loeb's long list of accomplishments at Harvard in science, physics, as well as his other duties at the Breakthrough Prize Foundation, I expect him to take us by the hand and show us the path. Avi, the floor is yours.
Thank you very much. So what I'd like to discuss today is well beyond Mars. Mars is really the very first step in exploring our cosmic neighborhood. With telescopes, we're able to see well beyond the solar system, and we have a very good view of the fact that about a quarter of all the stars in the Milky Way galaxy have a planet like the Earth with surface conditions that are similar to the Earth and potentially having liquid water on the surface and the chemistry of life as we know it. And so one of the fundamental questions is, are we alone? And one way to find out is by going places, not only within the solar system, but beyond. And the reason this question is important is not only to figure out our place in the universe, but also to figure out whether we are the smartest kid on the block. Because if we are not, we can learn something. It might feel like cheating in an exam. We might get answers to challenges from other civilizations, but it can also give us a better perspective about what they were accomplishing over the past billion years or so. Our technology is only, a century old, but if another civilization had 1 billion years to develop space travel, they may teach us how to do it. So there is also a practical benefit. And of course, going to the moon first and then to Mars are the baby steps in this journey to go beyond the boundary of the solar system. And that's what I'll describe in my talk. And you can see Mars here as one of the stepping stones to going beyond, first of all, the Kuiper belt, the surface that separates the solar wind from the interstellar medium, and then eventually going to the nearest star system. We live on Earth. It's a piece of rock that was left as debris from the formation of the sun. It is our home. We love it. It has beautiful life on it, but only for a while. Ultimately, in less than 1 billion years, the sun will warm up enough to boil off all the oceans on Earth. Clearly, we wouldn't be able to stay here beyond that. But well before that, there might be an asteroid impact, or we might change the planet in a way that would not allow us to continue staying on it. And so there are internal threats that could originate from non-conventional wars, climate change, but also external threats. And we should think more broadly. Currently, all our eggs are in one basket, and we might want to spread our civilization well beyond that. And of course, going to Mars is the first step. One thing to keep in mind is that we feel pretty comfortable here on the surface of the Earth, where the acceleration is 1g. Pilots endeavor in larger accelerations when they board a fighter jet, for example. But if you were to board a spacecraft that accelerates at 1g, it actually can bring you to the speed of light in 1 year. That's an interesting coincidence. The problem is that you need a lot of fuel for that, and it's not practical. But if you were to board a spacecraft for a year that accelerates at 1g, you would feel just as if you are here on the surface of the Earth. It would feel very comfortable. According to Einstein's theory of gravity, there is no difference between a gravitational force and an acceleration of a spacecraft. If you board a free-falling elevator, you don't feel gravity because the elevator is falling together with you. So in principle, the opposite effect from a spacecraft accelerating at 1g would feel just like the force of gravity on the surface of the Earth. And if you do that for 25 years, you could in principle cross the entire universe, because you will get very close to the speed of light. As I mentioned, we know of many planets now around other stars that are in the habitable zone. That's the region around the star where the surface temperature of rocky planets is similar to the Earth, and liquid water may exist. We don't know if any of them has life, and there are ways to remotely sense those planets. But another approach would be to travel to the vicinity of other stars and figure it out from up close. Of course, to have liquid water, the planet also needs to retain its atmosphere, because if you take water ice and put it in space and warm it up, it goes directly into gas phase. We know that from comets. The cometary tails carry the gas, the gaseous water vapor that is a result of warming up of the surface of the comet by the sunlight. So in order to have liquid water, you need an external pressure, and that is provided by an atmosphere. Mars lost the atmosphere. That's why we don't see liquid water on its surface right now. And the idea would be to visit a nearby star. The nearest star is Proxima Centauri. It does host a habitable planet, interestingly, that was discovered just a few years ago, Proxima b. The problem is that it's 4 light years away. So it takes light 4 years to travel from us to that planet. If there is anyone out there, they don't know yet the results of the 2016 elections. And this particular star, Proxima Centauri, is a dwarf star, the most abundant type of star in the Milky Way galaxy. The Sun is unusual. It's not the typical star that you find out there. Proxima Centauri is the typical star. It's about 12% of the mass of the Sun. And it has this planet, because it's much fainter, because it's a dwarf star, the habitable zone is closer in. So this planet is 20 times closer to the star, and it actually has a permanent night side and a permanent day side. Because of its proximity to the star, we believe that it's tidally locked. So my daughter said, if we ever go and visit that place, she would like to have 2 homes, one in the permanent night side where she would sleep, and the second in the permanent sunset strip, where you would have sunset forever. And that's where she would have her vacations. The problem is that if you want to reach that planet within our lifetime, it requires the spacecraft to move at a fraction of the speed of light. So in order for the journey to be 20 years, the spacecraft needs to move at a fifth of the speed of light. And the question is, how can you do that? And of course, if we consider other stars, it even takes longer than that. There is a system of 7 planets around the TRAPPIST-1 star, which is a little bit farther away. But as I said, Proxima b offers the prospect for very high values of real estate along the Sunset Strip. Oops. So just a few words about myself. I grew up on a farm in Israel, collected eggs every afternoon, drove a tractor, and eventually got to Harvard, and now I'm the chair of the astronomy department there. But about 4 years ago, I was approached by Yuri Milner, an entrepreneur with a physics background from Silicon Valley, who encouraged me to think about the possibility of visiting other stars. And he asked me to come up with a suggestion for how we could do that. And within 6 months or so, it looked like there is only one technology that can do it, and that's the technology we are now exploring in the project called Starshot. And it's basically a light sail technology. So how do you launch a spacecraft to a fraction of the speed of light? If you were to use fuel, as we often do with chemical rockets, the problem is that you are limited by the exhaust speed. You are limited to that speed times some logarithmic factor that includes the mass of the fuel relative to the mass of the payload. So you cannot really reach much more than several tens of kilometers per second, and that's pretty much the speed that all the space missions reached. Since Sputnik until New Horizons, the speed didn't change much. And it's basically a limitation of the exhaust speed, the sound speed of the material that leaves the rocket. And the only way to overcome that, and by the way, 30 kilometers per second is 1% of the speed of light. So if you want to reach at least 10% of the speed of light, you need to increase the speed of the spacecraft by a factor of 1,000, 3 orders of magnitude. That's more or less the factor by which technology evolved since Ford's T-car until Sputnik. So that's the factor of 1,000, and we are, and it took of order 50 years, and it's about time for us to enhance the speed that we reach by another factor of 1,000. So what is the trick? The trick is to leave the fuel behind and use a sail that is pushed by light. And since it's pushed by light, it can in principle reach the speed of light. This technology is called a light sail, and it has been explored in the past. But in order to reach 1/5 of the speed of light, you really need to use a very powerful laser of the order of 100 gigawatt in power over a few minutes. And by the way, this is roughly what was needed for the liftoff of the space shuttle. So it's the same amount of energy, the same amount of time that it took for liftoff of the space shuttle, except it's delivered to a single gram of material. So the idea is to have a very lightweight sail that weighs of the order of a gram or a few grams, have some electronics attached to it that includes navigation, communication devices, and a camera. And all of this can be packaged in a gram nowadays already. And then the spacecraft itself will not be very expensive. It will be roughly the cost of a cell phone. Most of the expense is at the infrastructure needed for the launch, the very powerful laser beam. And you can see an illustration of how, an artist's illustration of how this should work. The idea is that there is a mother spacecraft up there releasing a sail, and then a lot of low-power lasers produce their beams that combine together into a coherent beam that is focused on a scale of a human height, roughly a few meters, and pushes the sail over a few minutes to a distance that is 5 times the distance to the moon, until it reaches 1/5 of the speed of light in the direction of the target. And the target could be Proxima B, but it could also be targets within the solar system. It would take such a spacecraft only 3.5 days to reach Pluto, a task that took 9.5 years for New Horizons. So the NASA administrator changed between the launch and the time that New Horizons arrived. Here it will be in the same week. And if there are targets of interest, like a passing interesting object, we could chase it quite easily with this technology. The idea is that once the camera arrives to the, let's say, Proxima B, to that target, it transmits a photograph back towards the Earth, and then a very large set of detectors or a telescope obtains the image. That's a very challenging proposition, and we listed of the order of 25 technological challenges that include many aspects of the project, such as producing a coherent laser beam, making the sail out of material that is strong enough, yet lightweight, designing the shape of the sail such that it will ride in a stable fashion on the laser beam, and of course the electronics and the communication back to Earth. So we are currently in the process of research and development, trying to figure out whether these challenges can be met. And it's an exciting experience to be involved in this project. The main challenge could be policy, because obviously the same laser system could have other capabilities. And one may worry, for example, about the impact of atoms or dust particles along the journey. Turns out that with a relatively thin coating, one can protect the spacecraft from those. So it's not a significant risk. And so the plan right now is to dedicate the next decade to a proof of concept addressing the main challenges of the project, and then get to the second phase where perhaps if everything looks promising, one can construct a prototype of the system and eventually construct the actual system. Now, why aspire to go places very far away? Because in principle, it gives us a better perspective about life in the universe. And I often say to my students in class that looking at the sky teaches you modesty, if you are not already modest enough, because you realize that there are 10 to the power 22 habitable planets in the observable volume of the universe. That's more than the numbers of grains of sand on all beaches on Earth. So if you think about human history, there were kings and emperors that boasted after conquering a small piece of land on Earth. And that's similar to an ant hugging a single grain of sand on the landscape of a huge beach. It's ridiculous. You cannot be proud of that. Now, there is also the practical context, which is there might be a smarter kid on our block. And if we ever establish contact or find evidence, it could be a civilization that is not alive anymore. And I call that space archaeology, basically looking for evidence in the form of burned up surfaces of planets that were covered by photovoltaic cells, looking for the products of a nuclear war that may have taken place on a planet, looking for equipment, technological equipment that may be defunct, that is not communicating anymore. Sort of debris that was left out, just like Voyager 1 and Voyager 2 will become in a while. We will not really benefit from communicating with them. And so there are many ways to find artifacts out there, and one can even look for megastructures. And the idea is that we may learn something in the process. We may learn to better behave with each other, not to initiate a nuclear war, or to monitor our planet and make sure that it's habitable for as long as we can make it habitable. But also learn about technologies. It may well be that biological life is just a phase that eventually, as we witness, robots with artificial intelligence and 3D printers will basically rule the future. And one way to find out is to see these technological entities flying in space that were created by other civilizations that are much more mature than we are. And there happened to be the very first object that came near the Earth that we identified as originating from outside the solar system. We discovered it just a year and a half ago. It's called Oumuamua because it was discovered in Hawaii. At first, everyone thought that it's just a rock, but then we figured out that it's very weird. It's nothing like the comets or asteroids that we have seen before, that were born in the solar system. It's much more extreme in its shape, at least 10 times longer than it is wide. And so in a paper, we suggested that maybe it is a solar sail from another civilization. It turns out that we can search for such things from outside the solar system as meteors. Just a month ago, we wrote a paper with an undergraduate student at Harvard where we analyzed the data on meteors and found one that could have originated from outside the solar system. So we can find things that come from outside the solar system that visit us. And most of the time, it might be just like walking on the beach and looking at seashells that were swept ashore. But every now and then, we might find a plastic bottle, sort of a message in a bottle that we haven't anticipated. And so we should keep an open mind and not pretend that we know the answer in advance. As I often tell my students, science is an opportunity to maintain your childhood curiosity. You don't need to pretend that you know something. You're given a position, you're given a tenure position at the university to be able to explore and make mistakes and check what is out there without worrying about your job. And the mainstream of astronomy is searching for microbial life, evidence of molecules in the atmospheres of planets that might be indicative of primitive life. But if you look at life on Earth, and in fact we are finishing a textbook on this subject, on the subject of life in the universe right now, if you look at life on Earth, making the first cell out of the soup of chemicals was much more challenging than making a complex form of life out of the first cell on Earth. And so, to me, it's obvious that one should check for both primitive life and intelligent life at the same time without prejudice. We can search for all kinds of artifacts from other civilizations. For example, the city of Tokyo is visible at the edge of the solar system. So if there is anything producing artificial light, we could detect it out there. We could search for oxygen in the atmospheres of planets, but we can also search for industrial pollution. And it could be a signature of a terraforming civilization. But there is a fundamental question. Where is everybody? We haven't seen evidence so far. That's called Fermis Paradox. And one possibility is that these civilizations, based on the way we behave, are short-lived. They think short-term, and they produce self-inflicted wounds that eventually kill them. But even in that case, we can still do space archaeology and find artifacts of these dead civilizations. And my hope is that finding dead civilizations will inspire us to behave better and get our act together. And another hope that I have is that once we exit from the solar system, we will receive a message back, "Welcome to the Interstellar Club." And we will figure out that there is a lot of traffic out there that we were not aware of. Thank you. I'll be glad to answer a few questions. We still have 2 minutes.
Exactly. I'm a strict taskmaster, so 2 minutes. Grab your chance now.
Hi, how you doing? My biggest question for you, I've been a big fan of Project Starshot for a while now. Of the recent breakthroughs that you were just discussing that you foresee that need to happen over the next decade or two during the R&D phase, which ones do you think would be the most problematic to achieve and circumvent, and why would that be?
The biggest challenge, one can think of designs of sails and materials that can make a very strong sail that is lightweight. One can also think about the technology needed to build a laser beam. To me, the main challenge would be communication. Because of the vast distance of 4 light years, the thing is that the transmission cannot be very powerful because there is limited amount of power on the spacecraft. And so the signal that will arrive at Earth will be very weak. And we're still in the process of figuring out how to deal with that. You will need a large detector, but we haven't figured out the solution as of yet.
Thank you.
One more question?
Going back to where you ended, looking at distant locations, do you see any potential of using telescopes or detectors at Mars pointed at Earth to look at a place where we know we have life as a way to teach or gain clues about how to look for life in other solar systems?
Yes, definitely. Our imagination is limited by what we know. And so, of course, first thing you want to know, I mean, if you want to go out to the street and try to anticipate what you might find out there, you look at the mirror. So you look at yourself, and then it's not a bad approximation. When you walk out the street, down to the street, you find things that look just like you. However, very often you find things that don't look like you and are quite different. And there is a risk that if you search only for things that look like you, you might be missing things. And so how can you expand your imagination? One way to do that is by creating synthetic life in the laboratory. And there are several groups trying to do that. That could have major benefits to medicine if we understand how to create life in the laboratory. And we are just starting in this process, but one of my colleagues at Harvard, Jack Szostak, is on his way. I mean, he's already a Nobel laureate, but he's working now on producing a synthetic cell in his lab. And he says that working on this problem for several years convinced him that here on Earth, it arose spontaneously. He thinks that understanding how to make life in the laboratory enables him to figure out or be much more positive about the prospects that life emerged spontaneously. And if you think about making cakes, for example, you can start from the same ingredients and mix them in a different order over a different period of time, and you get a completely different cake out of the same ingredients. Earth produced life in one way, right? It's quite possible that there are many paths to making living organisms, and we could explore those. There is no reason why we should assume that there is only one, and that's the only one that can be realized. And so one way to find out is by going out to space and finding life elsewhere and seeing if it's the same as ours. But another is doing it in the lab and then improving your ability to forecast where in the sky you should look, under which circumstances you might get life that is different than the one that Earth produced.
Thank you.
Thank you. Those are deep thoughts.